This is Chapter 6, Soil Structure Interaction. In all directions in soil dynamics, this direction, soil structure interaction, or we say SSI, is the newest one. It's only developed in last century, 60 to 70. And this direction is to study the mathematical model, mechanical mechanism, coupling effects, and interface characteristic and calculation, and analysis method of soil structure dynamic system interaction. To solve the dynamic coupling problem of various media, and provide theoretical basis and analysis method for dynamic analysis and dynamic reliability design in many fields, such as structural engineering, geotechnical engineering, and underground engineering, protection engineering, and some others. And the research in SSI, soil structure interaction, the research object is in the seismic wave field, high-rise building, large bridge and underground structures, and large dams, and so on, connected with the foundation or surrounding rocks in the given input wave field. And the dynamic response of the structure and its surrounding soil is studied. Because all this structure surrounded by rock and soil, and the dynamic properties of rock and soil will affect the dynamic behavior of these structures. Then, if you want to the real dynamic response of all these structures, first you must know the interaction mechanism. And the dynamic interaction problem includes the vibration waves from the vibration source is transmitted through the soil layer of the site and input into the structural system to make the structure vibrate. At the same time, the inertial force generated by the structural system acts on the site in turn like a new vibration source, causing a new ground vibration to act on the structural system again. Then this just the interaction, soil and the structure interaction. Here let's see some system. You see a building, a frame building, or we say it's an upper building set on the soil, and the soil is layered soil. At the bottom, we can find bedrock. When the earthquake occurs, the earthquake wave will transform from the fault to the bedrock, then to layered soil, at last to the structure. This is the system. In the beginning, before we know the soil structure interaction, we take the soil as a rigid body. Then we applied the earthquake wave on the rigid board, like a base of the upper buildings. And upper buildings we can describe by some mechanical system. For example, here we give a spring and damping to describe the upper structures. And we can also describe the layer or floors of the structure. We use mass point to describe each floor, and use spring and damping to describe the connection between the different floors. And then we can analyze the response of the upper structures. But in fact, the soil, layered soil, will have a deformation, not like a rigid body. Then this assumption is not right. That means use this method, we couldn't get a real result. And if you want to consider the earthquake wave transformed in layered soil, then first we will calculate how the wave transformed in the soil. We know the wave in the bedrock. Then we calculate how wave transformed in layered soil using the physical and the mechanical properties of the soil. Then we create the model. We create the model C. First, we consider the layered soil system and calculate the earthquake wave transform from bottom to the ground surface. And we can calculate earthquake wave on the ground surface. Then we use this earthquake wave to shake the upper buildings to get the result. Although we already considered the response of layered soil, but this is not a real soil structure interaction. It considered the soil and upper structure respectively, no coupling, no interaction. That's not soil structure interaction. But now, if we want to consider this interaction, we have to build a general model with structure, upper structure, and the layered soil together. Then we input earthquake wave in the bedrock, in the bottom, and get the response of soil layer and upper structure. Then model D. This is a model considering soil structure interaction. Here, let's see some simple model of soil structure interaction. Let's see. This is a prototype model. A structure. We use mass point and a bar. This is a upper structure and is set on soil layer. Then we can simplify it into a model. Upper structure and the frame using a spring to describe the frame. And the lower, there's another mass point. In fact, this mass point is soil. And not only the soil mass, but also the stiffness of soil. We use another spring to describe the stiffness of soil. Then we create the simple soil structure interaction system. This model or this system can consider the soil structure interaction. But for the prototype model, if we divided the old model into two parts, upper structure and soil layer, into two systems, and we use soil system to calculate the earthquake wave on the soil surface, and we get earthquake wave on the ground surface. We use this wave to calculate the dynamic response of upper structure. Then this not soil structure interaction. Now let's see a complete system. A tall building set on soil layer, and there's a pile foundation below in the bottom of the structure. Here, we have to consider the soil structure interaction. Now let's see. It can be simplified to this model. This is the upper structure. We use some mass points and bar to describe the upper structure. Then we use a mass to describe the foundation. And below it, there's also some point. And this point with mass is used to describe the mass of pile. Now, when we want to consider the soil, first we have to apply a spring, a rotation spring, connect with the foundation and a rigid constraint. Then this spring can be used to describe the effects of soil surrounding the foundation. Okay. Then, because surround the piles, there's many soil. Then we use this point to describe the mass of soil layers, and use some viscoelastic model to describe the interaction between different soil layers, and the mass of soil connect with the mass of pile. Okay, then all this system are already used to describe the upper structure, foundations, and the surrounding soil. But the far field soil will also affect the dynamic response of this system. Then we also use some viscoelastic model to describe the effects of the far ground. Here, this is the model for a complete soil structure interaction. Or in soil structure interaction field, this model developed by scientist Penzer, and called this is a Penzer model. Now let's see a real underground engineering. This is underground engineering. For example, perhaps it's a subway or some other underground structures, and it's surrounded by soil. And then we can use finite element method to solve these questions. It's a kind of and any other numerical method can also use to solve this kind of problems. Here, this is a mesh of finite element method. In the center, this is a structure. Because structure, the stress is very high, and the strength is also high, then we have to use the small size models. But the soil far from the structures, we can use larger size elements. Between the larger size element and the small size element, and we have to use we have to change the size of element from smaller to the larger, and this is in the soil surrounding and the ground structure. Here's a special thing in soil structure interaction. In the joint surface between the soil and the concrete structure, in this joint surface, because they have a different stiffness, then in the same stress condition, they have different deformation or strain. Then perhaps there's a relative movement in the joint surface. Then in the joint surface, we have used special element. Later, I will introduce these how to deal with this joint element. Here, for example, this Goodman element. Goodman element is a kind of joint surface element. Okay. Or there's some other types underground structures. Let's see some mass of it. For example, this is an underground structure with 3 holes, or with only with 2 holes. That means 2 floors. Structure and the surrounding soil. And usually this underground structure is a tunnel. And this tunnel during this earthquake will have a deformation. And this deformation is along the axle, and we call it axial bending deformation. And this bending moment will cause the failure in the underground structures. Or in the cross-section area, there's also have a deformation. In for example, for underground structure with a circular shape, and it will change the shape in the earthquake. Or for the underground frame structure, it also have a shear deformation. In a cross section. And for this condition, axial bending deformation, we have to use 3-dimensional analysis. But for shear deformation of cross section, we can only use 2-dimensional analysis. Here, I show you some shear failure of the structure. This picture gives the pier of a bridge in failure in the pier of bridge in earthquake. We can find in strong earthquake, even the size of pier is very large, but there's also shear failure occurred in reinforced concrete. Usually, we consider that the underground structure will not have earthquake damage, but in fact, in some strong earthquake, there's also we can also find some damage in concrete in reinforced concrete structure of underground structure. Here, this is the piles of underground structure. We can also find the shear failure in it. Then, the soil structure interaction is very important for a seismic design of underground structure. Now let's see this picture. It's a building with a vertical parking layer. Usually the upper one with wall and windows, but the bottom layer, because it's used for vehicles parking, and the wall is not so many. And in this condition, the shear resistance is not enough. Usually in the earthquake, the failure will occur in the bottom layer for parking place. Of course, it's a kind of shear failure, and usually it's due to the weight of upper structures in earthquake. And there's also soil structure interactions in the geology failure. For example, if we make a retaining wall for highway, and in earthquake there's a slope failure or landslide, and it will generate a higher pressure acting on the retaining wall and cause the failure. Or in the pier or a bridge, a highway bridge with a pier. And in the earthquake, there's a large inertial force or soil pressure acting on the pier, finally caused the failure of the pier. This is a picture of the bridge pier in the slope. Usually in this condition, the acting force, the soil pressure acting on the pier is not easy to calculate, because when the soil applying the lateral earth pressure to the pier, then this pressure will cause the deformation of the pier. And this deformation will cause the additional pressure from the soil. Then this is a soil structure interaction problems, and we couldn't only calculate using some equations. That means we only consider the pressure of the soil to calculate the deformation of the pier, or we just use the deformation of pier to calculate the earth pressure. We have to solve this soil pier structure interaction problems in one time. Okay, about the soil structure interaction problems is also concerning with some hydraulic poured structure. You see, this is an earthquake dam, and this is a very large earthquake dam, and connect with the surrounding rock. In the earthquakes, we have to consider the deformation of the surrounding rock. Then we built the model as this. And this is a very simple model. It's a two-dimensional model. Concrete dam and the surrounding soil, and the far away free field effects. And this simple two-dimensional sample can solve the seismic problems, but it cannot consider all the soil structure interaction. You see, this model, this is a three-dimensional finite element method model. It can analyze all the soil structure interaction system. Then it can consider the soil structure interaction. Okay. Now let's see analysis system of soil structure interaction. And in this system, for the body, for the subject, only divided into three parts: soil, structure, and the joint surface between the soil and the structure. For soil, we have to know the soil dynamic behavior. Then we select or develop a constitutive model of soil. And usually we will use elastic model or non-elastic model. Obviously, for soil, elastic model is not valid. Usually we have to select some non-elastic model. For example, plastoelastic model or viscoplastic model, viscoplastic elastic model. And for structure, we have to know the structure behavior and use some constitutive model for the concrete. And we also can use elastic model and non-elastic model. And usually for concrete, perhaps in soil structure interaction analysis, if we concentrate on the soil, perhaps for structure, we can use elastic model. But now we have developed many good model for concrete, non-elastic model. And for joint element, first we have to know the contact behavior in the joint surface. Then we developed some contact model and used in the analysis. System analysis of soil structure interaction involves three problems. First is the characteristic and input of ground motion. This is very important. It's a dynamic load. The second is constitutive relation or constitutive model to describe the dynamic behavior of soil. Then algorithm. We use different methods to solve these questions. First, let's see ground motion and ground motion input. There are three elements of the earthquake motion. First is duration of ground motion. That's the time. And the characteristic of ground motion intensity usually is amplitude of this motion. And a spectrum characteristic of ground motion. That's the consists of different frequency in these waves. You see. Here I give you some, show you some earthquake waves. This is a time history of east-west acceleration, and the largest value is 2.1 meter per second square. Is about 53 seconds. And we can see there's many components of frequency. Then we make a Fourier analysis to get the Fourier spectrum of this time history of acceleration, and this is just the Fourier spectrum. And we can find the main frequency is in this part, about 2 or 3. About 2 or 3 hertz. Then this is another direction, time history of acceleration is south-north direction. The largest amplitude is the 3.4 meter per second square, and the duration is same, about 53 seconds. Then this is a Fourier spectrum. The input ground motion is the primary prerequisite for the study of soil structure interaction, and this including the first is the seismic fortification level. Is determined according to functional objectives. The second is ground motion input mode, and include determination of ground motion datum, where in which steps we input these waves, and input ground motion parameters on foundation boundary. 3 is input value size. At present, most of ground motion records obtained are surface record, but a few record of bedrock surface. And there are few strong earthquake records. You see, if we create a soil structure interaction system, usually this model, the bottom of this model is bedrock. Then we input the earthquake wave from the bottom. There's a bedrock. Then we have to use the earthquake wave we recorded in bedrock. And usually we have to make the structure to be firm enough to anti the strong earthquake. Then we have to use the strong earthquake wave to calculate the response. Then the strong earthquake records is very important, but it's not easy to get. Now we saw some record of earthquake wave. This is the earthquake wave. They have the different direction. You see, this is a pyre, and this is in the east-west direction, and this is a north-south direction, and this is up-down direction. For three-dimensional analysis, it's better to use 3 waves of 3 direction respectively. Now this waves is a velocity wave, not acceleration waves. And here, the bottom is the acceleration waves in three directions: east, west, and north, south, and up, down. And this is the waves, three waves for one earthquake. And these waves recorded in Wenchuan earthquake in 2008 May 12th, and is in Wenchuan, Sichuan province. And now we can compare the different record, the spectrum of it. Let's see the ground motion input mode. Just now I said at least three for three-dimensional analysis. But for two-dimensional analysis, we only need two waves. They are horizontal input of ground motion and the vertical input of ground motion, or horizontal two ground motion and one vertical input ground motion. At present, the standard stipulates that the vertical input is 2/3 of the horizontal input. That means if you only one horizontal curves, but when you calculate, you want to use two waves, then you can generate vertical waves using horizontal waves. And we just times the horizontal waves acceleration value, amplitude, times 2/3, then get the vertical amplitude. Then we can use horizontal waves and vertical waves for soil structure interaction system in two-dimensional analysis. Here, there's a different input method, and we can compare the different result of it. This is a high building with pile foundations, and we can simplify the model into this model. Upper is upper structure, the lower is piles, and is connected with soil. We can input the earthquake from the bottom of the bottom end of the pile. Input the earthquake wave there, and we can also input the earthquake in the bedrock, or we can input the earthquake in the ground surface. Now let's see the difference using these three different input methods. First line is the largest response displacement. We can find that the largest one is input from the bottom end of pile, input the earthquake wave. And the lower value is the calculation input the earthquake in the ground surface. It's too small. For the velocity response, the largest amplitude, the largest one is input from the bottom end of pile, and also the smallest value is the input in the ground surface. And the third line is the acceleration response, the largest amplitude. Now we find that the largest is not input from the bottom end of pile, but is input from the bedrock. And also, for the horizontal earthquake action, the largest amplitude is also the response using the input in the bedrock. Now, from this table, we can find the different input location will cause the different response result. Okay. Now let's see the determination of design ground motion peak acceleration. This is a picture of China. And we can find they divided the area into different area with different color. Let's see the different color representing the different peak value of ground acceleration. Usually, this we use the PGA. In earthquake engineering or soil dynamic, PGA means peak of ground acceleration. You see, the deepest color means the peak value of ground acceleration is 0.4 g. G is gravitational acceleration. And gravitational acceleration is 9.8 meter per second square. Then 0.4 g means is close to 4 meter per meter square. Okay. Then let's see. We are in Dalian. Now let's see how much it is. It's 1, 2, 3. This three color. We counted 1, 2, 3 here. In large area of Dalian, the PGA we use in seismic design is 0.1 g, about 1 meter per second square. Okay. And there's another picture. This is give the different the earthquake damage level. Different earthquake damage level. And in Dalian, this is not too high. It's 7 degree. Totally, we have in China we have 5 degree. For the seismic design, the old land divided into 5 level earthquake damage level. From 5 to 9. And here we have this is the determination of seismic ground motion parameters zonation map in China. And the peak acceleration provided by exciting probability in the seismic hazard analysis and the engineering side. In seismic design, we have to use these two pictures. Now let's see earthquake wave. We already know there's at least there's 2 waves. It's body wave, P wave and S wave. P wave is maximum velocity. P wave has a maximum velocity, and will first arrive to the structure foundations. The vibration direction is consistent with the propagation direction. It causes the ground to vibrate up and down. Because the earthquake wave is transformed vertically from the soil, vertically up from the soil. Then this P wave will generate up-down movement or up-down vibration. But shear wave, the vibration direction is perpendicular to the propagation direction and causing a horizontal shaking of the ground. It is the main cause of building damage in an earthquake. Usually it will cause the horizontal shaking and cause the heavy damage to the structure. There's another type of wave we call this surface wave. And there's two types of surface wave, loud wave and relay waves. When shear wave reaches the surface, it includes SH wave and SV wave. SH waves means it's a shear wave, but the vibration direction is horizontal. And SV wave is shear wave, but vibration direction is vertical. There's different waves. It is a mixed wave generated by the encounter of P waves and S waves on the surface of the earthquake. And we will discuss this surface wave in detail in chapter 3. Now let's see the motion of different wave. The upper one is compressional P waves or compressional or P waves. The vibration direction is same with the transform direction. And the bottom one is shear or S waves. The vibration direction is normal to the transform direction. Or let's see the simulation. For example, a man walking directly forward, but he lifted a body, and he moved this body with his working. When the movement direction is same with the working direction, is P waves. When the movement direction is vertically, then is S waves. Or the movement is rotate in a vertical surface, then is relay waves. If the movement is horizontally, is loud waves. Then using this picture, we can easily understand P waves, S waves, relay waves, and loud waves. When the seismic waves propagated from the depths of south reaches to the surface, its incident direction is gradually close to the vertical direction of the vertical horizontal surface. Usually it will occur. In general, the two horizontal components along the surface and the vertical components perpendicular to the ground surface are taken as the seismic acceleration. Seismograph, it can receive the horizontal and vertical vibration of the ground respectively. We can record the earthquake wave. Now, in the soil structure analysis, how to select the earthquake waves? According to the site condition, the frequency spectrum is corrected by adjusting the amplitude and the time scale of the measured seismic wave. The scaling of seismic acceleration amplitude does not change the spectrum characteristic and the duration. Yes, we can scaling the seismic acceleration amplitude according to the maps. Maps gave the PGA, according to the PGA maps, national maps of PGA. And adjustment of predominant period of seismic wave. The measured seismic wave is used as input, and the artificial seismic wave is sensitized based on the design. You see, sometimes we couldn't get a suitable earthquake wave recorded in the earthquake. Then we can use artificial seismic waves. Artificial seismic waves is generated or created by engineer according to some rules. And artificial seismic waves is sensitized based on the design response spectrum of the code. This code usually is anti-earthquake code, national code. And according to the seismic hazard analysis of the site, the peak acceleration and the different exceeding probabilities is given as the base input acceleration. Let's see the synthesis of artificial seismic waves. Here, this is generated artificial earthquake waves, and this is the spectrum of it. Now let's see. This is the standard acceleration response spectrum curves of 4 types of site in the code. And the intensity is 8, and design ground motion is 1 group. And we divided the ground into 4 types. And according to the stiffness of ground. Then for different types of ground, we have to use different response spectrum. And this spectrum given by the national code. And this, the red one is the response spectrum curves of the same site with different damping ratio, and the intensity 8, and class 2 site. Here, 3 spectrum curves with different damping. Is from 0.05 to 0.1, 0.15, and 0.2. Then let's move to another part, is constitutive model and the elements of contact surface. This is very important. Here we don't talk about the constitutive model of soil and concrete, because we already learned this part in other course. For example, for the for the in soil dynamics, we have a special chapter to describe the constitutive model. In this lecture, is chapter 2. And for concrete, constitutive model is also introduced in the reinforced concrete. Here we only need to introduce the constitutive model for contact surface. There is a large shear stress on the intersurface between soil and the structure, which is caused by the inconsistent deformation of the two materials. You see, they have different stiffness, but they have the continual stress distribution. Then the deformation is inconsistent. It is very important to analyze the deformation mechanism of contact surface, the development of shear failure, and the process of load transfer, and to simulate correctly in the calculation. The study of contact surface deformation mainly includes two aspects. One is the constitutive relation of contact surface, especially the relationship between shear stress and shear deformation. The other is the contact element, which is a special element used to simulate the deformation of contact surface in finite element calculation. And the two aspects are interrelated. The contact surface element is used to express the deformation on the contact surface, and the expression of the contact surface deformation must adapt to the selected contact surface element. There are two forms of failure and deformation. One is tension cracking, and another is sliding. You see, now here is a direct shear test for soil structure joint surface. Upper is soil specimen, and the bottom is concrete specimen. And we can install some sensors in the concrete surface to test the stress in the soil. Then we can find if we use container, a box, we put the soil specimen in the box and let the soil contact with surface of concrete. Then we give a horizontal force that the soil specimen have a lateral movement, and we can find in the different location they have a different stress, shear stress. Then we can know that in different location they have different stress. Is not uniform. This test, this kind of test will the shortage of this test is ununiform stress distribution. And there's three types of shear failure in the soil close to the surface of concrete. The concrete wall is smooth, and the sliding surface is along the wall, as shown in the figure A. We can find This is the sliding surface is very close to the surface of concrete. And the wall is rough, and the sliding surface occurs in the soil near the wall. Then the failure is given in figure B. We can find that the sliding surface have a certain distance to the surface of concrete, and some soil will connect on the will fix on the rough concrete surface. The sliding failure is not around one surface, but many surfaces, forming a shear failure zone. This failure surface may have a certain angle with the contact surface, but on the macro level, the failure area is along the contact surface as shown in figure C. We can find the shear failure occurred in a belt. We couldn't find a significant one sliding surface in the failure zone. The interfraction condition of soil structure interface has great influence on the calculation results of dynamic system. So it is necessary to deal with the interface problem reasonably and give the reasonable contact surface connection condition. When you do a soil structure interaction analysis, the interface condition is very important. We must set the joint surface between the structure and the soil.